So it's a great pleasure to introduce this talk in this room called coreboot and open source BIOS replacement, I think. And this talk will be presented by Peter Stuge. Give him a well.
All right. So first of all, how many of you guys saw the talk last year I did about coreboot? Okay, maybe 15? That's good. I'm not going to repeat much, so I think this should be good also for you. Just a short introduction of myself and of coreboot. Then I want to talk about what goes on inside of coreboot, what and why. And the short answer is we have 30 years of history running in our PCs today, so there's a lot of stuff to take care of. I'm going to talk a little bit about the source code tree, what files are in there, what directories, what the code in each directory is typically for, something about the code flow at runtime. I'm going to talk a bit about development and what you have to keep in mind if you're going to add a new board to coreboot. I'm also going to go through what has happened in the last year in coreboot and also the very exciting project Serialize, the project cBIOS, libpayload, philo, and FlashROM and BIOS extract. Some utilities you may recognize from before, and some of them are new. Also, I'm going to say a few words about boot times because it's beginning to be more popular or more and more common to see boot times advertised, and it's important to be careful there. Conclusion, some thanks, and the normal ending with links and questions. My name is Peter Stuge, as you already heard. I'm from Sweden. I do consulting in software, hardware, and security. I like open source. I like low-level embedded things is always fun. I first discovered coreboot in 2001. I was working on developing a set-top box for my employer at the time. And I thought, okay, we should use this. We should use this open source firmware because we were building this set-top box on a PC platform, and I really wasn't interested in hacking assembly code, and rewriting a BIOS, which was the other option. Unfortunately, that's what I ended up doing, but I stuck with coreboot, and I'm still active. I tried to think that I'd like to think that I stayed mostly silent until 2006. And then I went to Hamburg at a developer meeting there and got involved a little bit more. Lately, I've been doing some kconfig stuff in coreboot and some work on the VIA VX 800 and 855 code. Also MSR tool and support and marketing. Coreboot is an open source BIOS replacement. It's written mostly in C, as opposed to many of the commercial BIOS sources, which are a lot of assembly code. It's one single code base, supporting all the chipsets and manufacturers and mainboards, about 200 different vendors and about 200 different components as well. Sorry, no, not vendors. 200 components and 200 mainboards from, I guess, I don't know, maybe 50 or so vendors. We have a 10-year anniversary this year. The project was started in 1999, so it's been around for a while, and it started out in the cluster computing world, but it's spread out, and it's really useful anywhere you have a PC or an x86 CPU starting up, and that's a lot of places now. Coreboot supports ACPI and system management mode for platforms that require this, and people that want it. I think it's important to remember that coreboot is not just an open source BIOS. It's not a standard BIOS. It brings a new concept. It separates the hardware initialization from the operating system load. And the traditional BIOS will do both of these. coreboot does just the hardware initialization, and it's new code, so legacy-free, no assembly, 32-bit mode. And the bootloader is isolated into its own program called a payload. The payload goes into the ROM image together with coreboot, and when coreboot is done running, it jumps to the payload, and the payload can't really jump back. There's a whole bunch of payloads. I've talked about them before. There's Philo, GPXE. You can use a Linux kernel also as a payload, and do lots of fun stuff with Wi-Fi or Fuse, or just boot from that old card you have without an Option Rom. Mem Test 86 runs as a payload. How many have used Mem Test 86 for something at some point? Yes, good. I'd say that was about 65%, 70% maybe. There's also a Windows CE bootloader and lots of other payloads. We also have a compatibility payload called CBIOS. Using that, you can boot BSD, and you can boot DOS, and you can boot Windows even, if you want to. CBIOS implements all the standard BIOS stuff and is an open source BIOS, whereas coreboot only does the hardware initialization. So you can combine these two, and then you get an open source solution, which is a really 100% replacement for your BIOS, in many cases. And coreboot is GPL2 licensed, but because we split out the payload, you can have a bootloader with any license. It doesn't have to be GPL. It's not linked together. It's really a standalone binary. We've created a C library, a very small C library, to facilitate writing payloads easily, called libpayload. And that library is BSD licensed, so you're really free to choose how you want to distribute your homemade payloads, which can be useful. It's nice to put, for example, an application as a payload. If you have a really simple one that doesn't need an operating system, it's going to be running pretty quickly. So what does coreboot do, or what does it have to do? I made this nice little graphic. This is a PC about the way it looked in 1980 when the first PCs came out. It's also when the first BIOS came out, because this cassette block here, that could be one of two brands of cassette players or tape players. And depending on which one you had, you needed to access it and program it a little bit differently. So the BIOS came in order to abstract these two tape players, and you just had one software interface that you could use to bootstrap the system. And this was in 1980, and we've gone from that to something more like this in a normal PC today. And there's a lot more stuff here. So this is showing what could be a 4-CPU AMD 64 system. We have the 4 CPUs, you see them up top, and there's a memory controller attached to each CPU. The memory controller has its own RAM, and besides the CPUs connecting to each other, there's also a north bridge somewhere, and a little bit depending on which CPU it is, the north bridge might even be integrated into the CPU. So either there's this connection, some kind of bus between the CPU and a north bridge. It could be a front-side bus. It could be just a local bus, meaning that the north bridge is actually part of the CPU. So it's a bus on die, if you want to, but there are no connections on the main board. Or it could be hypertransport. The north bridge has oftentimes now a graphics part with 1, 2, 3 video output ports of some sort, digital, and lots of bandwidth going there. And typically the north bridge also has a PCI Express connection. So this, and again, if the north bridge is integrated with the CPU, then the PCI Express might be coming directly from the CPU chip. There's also the south bridge thing with some functions. PCI bus, a standard slow old PCI bus, something called the SM bus, System Management Bus. I'm going to get back to that in just a bit. We have LPC, low pin count, which was created to replace the ISA bus. And PCI and LPC, they both look just like they were attached directly to the CPU. They still work the same way this bus does, as far as software knows, anyway. The South Bridge can have a PS2 port, and it can have an SPI port, or an SPI busmaster. And on the PCI, there's usually some USB or IDE, and, well, I guess both integrated. And then there's this guy, the boot flash. That's the flash chip where we have the firmware stored. Remember in the 1980s picture, we had a boot ROM up there. It was connected directly to the CPU. But nowadays, it's a little bit further away. However, it's still accessible when the system powers up. It's still there. The CPU fetches the first instruction when starting to execute. So there's when all these components turn on from reset, or come out of reset, they will be set up so that when the CPU accesses the special magic reset vector address, top of 4 gigs, it's going to be decoded to the boot flash chip down there, and all the components along the way have to play along. So this is connected to multiple places because sometimes it's connected to LPC directly, the flash chip. Sometimes there's this SPI busmaster inside the South Bridge, but sometimes there's also this Super I/O chip, which does a lot of other stuff. And it can have an SPI master over here, and then the boot flash can be connected through there instead, and over LPC, and yeah, all the way up. And this can be a lot of fun. During my time hacking on Flash ROM, I discovered that, okay, so decoding works by default. That's fine. It comes up the right way. But this SPI master, it's kind of limited. SPI supports 16 megabytes of address space, but one Super I/O vendor decided to save on 4 of those bits in their register space, so you can really only access half a megabyte of flash chips instead of 16. So that's too bad if you wanted to upgrade your flash chip. Back to this SM bus thing, and I'm also going to talk about why I color-coded this. I don't know how well you can make it out, but this is green anyway. That's probably easy to see. Most of the stuff up there is black, and there's some red over there, the RAM, that memory controller, the North Bridge, PCI Express, the South Bridge, these parts except for the LPC, which is black, and all of the Super I/O stuff, if it's there, is also red. And everything that's red in this picture is stuff that coreboot needs to touch and needs to configure. Whereas the black stuff just works on its own, and the flash chip is blue because, well, it's a nice color and it's a little bit special. That's where we are. But the red stuff, by far the most interesting challenge is this memory controller guy here, because this thick red line is getting getting a lot of development. It started out being connected directly to with the RAM chips being connected directly to the CPU, and now we have DDR3. And DDR3 I haven't read enough about that, but DDR2 at least is running so quickly that in order to do the RAM or the memory controller initialization, you have to use a brute force search to find the correct timing adjustments that the memory controller is going to use when it's talking to the RAM module, the DIMM, to compensate for how the mainboard was designed and how the tracks are laid out on the board. So that's a lot of fun, and it's getting really complex. And all of those, all of that configuration here at this memory bus thing is also highly dependent on the DIMM. So where's that information stored? Well, it's stored in these green little SPD boxes on the DIMM. Of course, we're here in the boot flash, but we're running in the CPU from the boot flash, and we have to go out on this green bus and read the contents of this small little EEPROM on this green SPD EEPROM to find out how we're going to program the memory controller so that it can drive that particular RAM module on the wide red link. And of course, we have to set up everything else as well. We have to set up they're also red, it's difficult to see, maybe, the hypertransport connections between the CPUs, as well as to the North Bridge, and set up the North Bridge so that it properly separates the PCI Express from what is supposed to go to the South Bridge. Address decoding and speeds, the link speeds need to be set up, and in the South Bridge, same for PCI, the PCI bus, and PS2 is comparatively simple. SM bus needs a bit of setup. You need to wait until there's a stable clock on this green bus. Super I/O, all of these functions, they have, most of these functions, let's see, serial, parallel, watchdog, maybe GPIO, and the floppy drive anyway, they have I/O ports that need to be set up, and they have interrupts that need to be set up, and they might even have a DMA configuration that is necessary to be programmed elsewhere in the system so that whenever something happens over here, the CPU will actually notice. So that's the coreboot task. And in the source tree, there's a couple of subdirectories, 4 at the moment. There's been a lot of restructuring over the last year, maybe, pretty much over the last year. I'm going to talk a bit about that soon. But some examples of files you can find in the source tree. You have first of all, the source directory. That's the big, that's where all the fun stuff is. It has a couple of subdirectories: CPU, Super I/O, console, North Bridge, South Bridge, mainboard, devices, lib. It probably has a few subdirectories still, more, but these were the most interesting ones, I think. For example, that CPU x86 16-bit reset 16 inc, that's the reset vector, so that's the very first instruction that the system is going to execute when it comes out of reset. It moves on, and then it comes to the cache as RAM file, and both those two files are written in assembly language, but those are the only ones. Cache as RAM, how many know about cache as RAM? About 10, okay. So cache as RAM is a neat trick in Pentium processors and later. The reason these are in assembly is because there's no memory, right? We need to configure this wide red link before we can actually use some RAM. And C code or C compilers are they rely on RAM being available and RAM being online, connected, running. So we can't really compile any early code with a C compiler because there's no RAM, so the code won't run. And the trick is to use cache as RAM instead. So we're using part of the cache memory, which is on the CPU die, as RAM. You can set it up so that it doesn't clear and invalidate the cache, clear out the memory, or clear out the contents. And you don't have a lot of space, but you have enough to actually run C programs if they're carefully built or compiled. So the next file, for example, is Super I/O IT8712F. That's the Super I/O chip. called IT8712F early serial.c, and it does exactly what the file name says. It enables the serial communication so that the serial port on, well, let's see, over here, is usable from coreboot. And then the console driver uses the serial port to start talking and helping us figure out why nothing is working. Then comes the RAM initialization, and that's the fun part. That's in Northbridge AMD K8, RAM init F. So the F here is for family F, the AMD 64 CPU family. And this file is some 90 kilobytes right now. So it's pretty big, but it's a lot of comments as well. Once RAM initialization is set up, there's some stuff that happens in between. Finally, or eventually, we might end up running this Southbridge via K8T890, K8M890 Chrome.c file, which is sort of a coreboot initialization driver or a coreboot driver for the graphics, the onboard graphics part in this chipset. This one. And we get some graphics output. The order in which this Southbridge Chrome file and other files and also the RAM initialization is executed, that's controlled by this Devicetree .cb for coreboot file, which describes the mainboard, what components are on there, how are they connected. And later on, we get to run through the generic hypertransport code, which sets up all the hypertransport connections in the system, the links between the CPUs and links from the CPU to any other bridge, be it Northbridge or Southbridge. And the same goes for PCI devices, of course. All the PCI buses need to be enumerated, and there's some code there in devices, PCI device, to check for what's on the bus, what's connected to the bus, and to set it up so that it's working. There's also a lib directory, which has various bits and pieces, string functions, and also this USB debug direct driver for the USB debug port. Maybe you don't have the Super I/O, but oftentimes you have USB, and in USB 2.0, the EHCI spec, there's this debug port function where you can actually communicate over USB without DMA and only using PCI config space accesses, which is really easy, and you don't, again, you don't have to have RAM initialized to do it, so it's a good debugging method. Finally, there's a whole bunch of kconfig files. There's one in every subdirectory. Kconfig is the configuration tool from the Linux kernel, and we want to use that as well. It's a nice configuration method, I think, or configuration user interface. So this is it, the source code, basically. The devices subdirectory, again, that's used for the device tree that coreboot builds at runtime. It checks all the stuff that's connected in the system and builds this long list of devices, and then there's some generic code to deal with each class of hardware. So this is source, and that's good. The kconfig files are used with the kconfig system, but kconfig was introduced fairly recently in the current codebase. And before that, we used the targets subdirectory quite a lot, and for some mainboards, it's still necessary to use that. There you create this, first of all, a subdirectory for the vendor, in this case emulation, because it's an emulated vendor, I guess, and then you create the board name subdirectory, in this case QEMU, and finally you put a config.lb file there, which you fill with some settings for how this board is going to, or for how coreboot is going to be built for this board. Number of PCI slots and stuff like that. So again, this was used only for the previous configuration method, but it's still necessary in some cases because kconfig isn't quite there for all the boards yet. And two more directories, documentation, it's what it says, and utils for utilities. So we have some utilities that are really central for coreboot, for example, CBFS tool, which I'm going to mention a bit more about in a bit. And there's a whole bunch of other utilities there as well. So I mentioned configuration and build this config.lb file. The old way to build something or to build a coreboot for a board is to go into this targets directory vendor board and make some changes in this config.lb file so that it matches your needs. Maybe you want to change the resulting the file size for the resulting coreboot.rom file if you have a flash chip which is different size than the default for this board. Then you have to go up a few directories and you have to run this build target command, and then it generates a whole build directory with makefiles and everything, which is named by a parameter inside this config.lb file. So then you have to go down to that subdirectory and run make, and then you get a coreboot.rom file. Oh, that's right, you specify the payload inside config.lb as well, which payload file you want to use with this coreboot. And there can be only one with the old build system. And it worked, but it's not so fun to deal with, I think. It still works, but the new way I like a lot better. Make menu config and just change the settings and run make, and then you get this coreboot.rom file. It's a lot nicer. So the code flow at runtime, I talked a bit about it in the source tree, or connected to the source tree. First thing that happens is enter protected mode, enable caches RAM, console output again, and go over the hypertransport or the most central components in the system, initialize them, set up the speeds. For hypertransport, for example, you have to also do a reset. Here, you set the frequency you want hypertransport to run at, and then you reset. And when you reset, it comes up with a higher frequency. And then you do the first things again and check, oh, okay, now it's running quickly. Then I skip that step and I don't reset again. Coreboot supports a fallback or normal scheme where you can actually have two sets of your firmware inside the same flash chip. And after the early initialization, that's decided upon which path to follow. So you can have a really safe updating method by only replacing the normal image. And if it doesn't start properly, then next time you reboot, coreboot will start the fallback. Next step, initialize Ram. Do all the hard work, talking with the green bus, going all the way around and fetching the parameters and from the memory modules and setting up the memory controller so that it's possible to uncompress and run the coreboot RAM part of coreboot, which doesn't seem to do much, but what it does is kind of complex. It allocates all the resources, divides up the address space in the CPU, and shares it, or so that it's shared between all the devices in the system. So the PCI and the PCI Express and all the rest of the stuff that needs to be configured, I/O ports and interrupts and DMA and that code is generic, and you don't really have to change it per board. So that's nice. But sometimes the main board requires some specific configuration as well. Maybe there's this odd function on this main board, only on this main board, and you have to do some manual setup or resource allocation for that. After that, next step, coreboot creates some tables which it leaves behind in RAM for whoever comes next, for the payload and or for the operating system. There's the coreboot tables, which is our own table format for providing information about the system. Stuff like memory, how much memory is installed and how it is configured, and what memory regions are used by whom, and what memory regions are available for use by the operating system or payloads. ACPI tables, if the particular board supports them, MP table for interrupt routing, and PIRQ table for interrupt routing as well. DMA, sorry, not DMA, DMI, with the information about this firmware, if there is one, or maybe about the particular system even. And final step, jump to payload, and then coreboot is finished. So what's the recommended procedure for getting a new board to run coreboot? This is what we suggest. Find a similar board, which is already supported by coreboot. Just build the firmware for that, flash it onto the board, and see if it works. Sometimes it actually does work. Of course, if it doesn't work, you need a good way to recover. So don't forget to have an extra flash chip, or maybe a ROM emulator, even that's even better. So for this to have any sort of chance at success, you need the CPU and the North Bridge and the South Bridge and the Super I/O to really be the same as the other board. But many times they are, because all the vendors, they have reference designs, and many mainboard designs are really just copies of the reference design with a few small variations. And that means you get lucky, you can get lucky, and it's really easy to add a new board. Next step in this saga is to update the devicetree.cb file, wherever it is in the source mainboard vendor board subdirectory, to reflect this particular board, this particular PCB design. So how are things connected together? What PCI addresses or device IDs do the different devices have? That's also where you change the Super I/O if there's a different one. And the Super I/O is pretty easy to just replace. You have to say, okay, this board is using not the ITE 8712, but the 8716 or something, and then it might just work. First step is to get serial output going. That's it's just really painful to try to debug without having that. And worst case, you have to add some new code in for the CPU support or the Northbridge support, maybe the memory controller. If this board has a new CPU, or well, not a brand new CPU, but at least same family, but a new revision, maybe there are some changes that need to be made. Or you're using some RAM type which wasn't already supported by the RAM initialization code. That might need to go into the code base somewhere to properly set up. Then set up or create an interrupt routing table. Also goes into source mainboard. Start with a PIRQ table. It's possible to read that with one of the utilities called getPIR, I think. You can read that out from the BIOS, the factory BIOS, but sometimes, oftentimes, it's not really correct. So you might have to do some manual fix-up, because most operating systems today, if they find ACPI tables, they're going to ignore this PIRQ table. So the BIOS vendors, they don't bother making sure that the PIRQ table is correct. They just focus on ACPI and keep I guess, the old copy-paste PIRQ table in there. But PIRQ is a lot simpler than ACPI, so it's a good idea to start there and then deal with ACPI later. When everything looks like it's in good order, you add a call to this RAM check function in coreboot. It's a really simple test. It's, I guess, even more simple than the factory BIOS RAM tests if that's possible. But it's still a way to see if the RAM seems to be in working order. And the final step, of course, is to get the payload started and then get it to function. Mem Test 86 is really what you should start with and make sure that the RAM configuration is solid. Now, if you didn't need to do any of this code addition over for the RAM controller, then Mem Test 86 might just run fine the first time. But certainly, if you're adding or changing some of the code in for the RAM controller or the memory controller, then it's important to do thorough testing so that you squash any bugs that might remain. It's actually fairly frequent to make it all the way to RAM check, and sometimes also even past RAM check without RAM actually working properly. So sometimes we get some mails on the list where someone has tried to get a payload or tried to boot a new board, and it looks like coreboot is doing everything okay, and coreboot is good, but the payload doesn't work or doesn't start, and that usually indicates a RAM problem because there's a lot of caching going on, and it could be that all the code is running from cache, so that there wasn't any need for RAM until the point where the payload is supposed to be started, and then it blows up. So yeah, it's setting up the memory controller again is by far the biggest problem. And okay, moving on to what has happened in 2009. In coreboot itself, finally, it turned out that the version 3 codebase, which was pretty much started in 2006 in Hamburg, it really doesn't receive any development attention or developer attention anymore. It's slowed down. No one's really working on it, but it's still there. And starting out with version 3, we focused on the GeoDLX because we considered it a simple platform to start with. And that means that version 3 really has the best support for the AMD GeoDLX. So, and there are several users who have GeoDLX designs and GeoDLX products that are using version 3. So it's not a waste at all. But it turned out that it would probably be a better idea, and in any case easier, to pick up the old version 2 code and try to move it forward instead of starting from scratch. So the work on the version 2 code continues, and now we just call it trunk. Yeah, I think there's a version 4, version number 4 committed somewhere in some define, but it's not officially version 4 just yet. And we want to take all the good stuff that we came up with for version 3 and put it into the trunk. So kconfig, I already talked about that. I think it's really important because the old configuration and build system just wasn't really pleasant, and it helps a lot to have this familiar interface when you're starting out. And personally, I think it's really convenient as well. Another big deal, big improvement from the old version 2 structure is what is called LAR in version 3, and the same concept is called CVFS in the current source. So LAR is short for Linux BIOS Archive, and as you may know, coreboot was called Linux BIOS earlier, but we changed the name last year because, well, it was meant to be Linux always, but it wasn't Linux always, and it's certainly not a BIOS. So we thought we should go with a better name. We renamed LAR to Little Archive at the same time, but well, again, we changed a few technical parts of the specification also, and decided to go with a new name at the same time. So it's called CBFS. That's, of course, coreboot file system. And it's a file system for the flash chip. So the flash chip where you have the firmware is made up of a bunch of files. That's also the way all the factory BIOSes work. They have some simple kind of flash file system too. CBFS has a fixed location boot block, which is at the end of the file where the reset vector is supposed to be. It's currently also fixed size, 64 kilobyte, but there's some work to be able to have a dynamic boot block, making it just a couple of 100 bytes in size. Because if you have a smaller flash chip, it's nice to have those extra kilobytes, and even if you have a large flash chip, maybe they're just what you need in order to fit that nice payload in there. Besides the boot block, there are the coreboot files. So coreboot really is made up of two files inside CBFS. The first one is the ROM stage, which is the part running, setting up caches RAM and setting up the RAM initialization. We're doing the RAM initialization. And the next part is coreboot RAM, which does all the thorough device enumeration, scanning the system completely for all the devices that are connected and configuring them and doing the resource allocation and so on. Besides that, there are the payloads. Of course, payload or payloads if you have many. And into the CBFS you put the VGA BIOS as well if you have one. And you can also put Option Roms if you want to use those with CBIOS. We had a Summer of Code project with, well, 3 projects in Summer of Code. One was the GeoDLX VGA BIOS project, creating a VGA BIOS ROM for GeoDLX, which is open source. So the ROM is open source. There was a VGA BIOS from AMD, but it was, I don't know exactly why, but I guess they had licensed some parts of it from someone else, and they weren't allowed to open source it, even if they wanted to. And that project, anyway, it was finished, it's working. There are patches for the CBIOS, VGA BIOS. There's a VGA BIOS inside CBIOS, or part of CBIOS. Another project was a USB Option Rom to be able to boot from USB devices on systems where you don't have a bootloader which supports USB natively, and I only know of Philo which does. So this seemed like a good idea. It would be nice to use with CBIOS, of course. It would also be nice to use if you have an older system without USB support in the factory BIOS. You could use this, somehow get it to initialize in the system. There are a few ways, and be able to boot from USB also on really old mainboards. Unfortunately, this project, it wasn't so successful. Maybe it was the wrong approach. And we have to rethink that a bit, how to best be able to boot from USB in all the cases. And then we had a comeback, or a sequel to the last year, the project from last year's Summer of Code called AVAT. Cristi Magherusan from Romania, he worked on getting coreboot to do all virtual all the time, or getting the PC to do that. By having coreboot start a Linux payload, a Linux kernel payload, which together with KVM tools go into the flash chip, so that you have the basic hypervisor in your system running directly from boot time, and any operating system kernel that you're running, or any operating system image that you're going to run in the system, will be virtualized using KVM. And he had some issues last year running into how UCLibc implements thread local storage, and finally that was solved this year. So it's actually working, and it's really nice. It requires a bit bigger flash chip though, but it works, and it's a really nice project, I think. We had some vendor developments this year. AMD engineers, they worked on coreboot support and developed coreboot support for the AMD RS780 and SP700 chipset products. It was finished sometime this summer, maybe even late spring, but I guess the last bugs fixed in the summer, as we understood. And then the code needs to go to the AMD legal department for review before they can release it, because it's going to be open source, and they need to check if it's okay to release this code. And it's still there, unfortunately. Now, next year, in a few months, AMD are going to come out with a next generation chipset, the RS880 and the SP800 combination. And it's, of course, unfortunate that once more we don't have the code until the chipset is nearing end of life, but what to do? They released documentation really fairly quickly, even before they released the code, or even before they developed the code themselves. But unfortunately, it's not really helpful enough. The documentation from vendors never really is. You need a lot of extra knowledge, which typically is only available from the FAEs, the field application engineers working for the vendors, and usually open source projects don't have the right connections to reach these engineers. But we're working on that as well. AMD is really a good player. I think they're participating on the mailing list and are being friendly. I'm just sad that the code has been stuck for so long. When it comes to VIA hardware, we got some code contributed by the OLPC, the One Laptop Per Child project. They sent us code for the VIA VX800 and the VIA VX855 chipsets, which the 855 I think was released this summer. So that's really nice, and also the Nano CPU support. It's the typical open source vendor tragedy where they work parallel with the project instead of working together with the project. So when they release the code, it's based on 3 months old trunk. So this code base needs to be sort of unified for the VX800 and 855 and then forward ported so that it can be merged with the current trunk. And on the Intel front, we don't really hear much from Intel themselves, but we've heard from a couple of companies that are working on Atom and Intel 945 combination platforms. They've sent a couple of questions asking about, well, my payload seems to not be running right, and they haven't sent any code, so all we can say is, well, check memory in it. It's probably the problem. So hopefully they will also release some code eventually. Another fun thing that happened in 2009 is we got the cover of Linux Journal magazine and a really good article in there about coreboot and how you can get started running coreboot in QEMU. So that's the October issue. I think you can find the article online by now. And we're going to have a dev room at FOSDEM. That's going to be fun. And I don't know, maybe a coreboot conference. How many of you guys would be there if it was in Northern Europe somewhere? So, okay, a few hands, 4 or 5. It's good. Related projects, Serialize. This was an idea that a couple of guys had during the Embedded World, well, we discussed it anyway a lot during Embedded World in Nuremberg in March, and 1.0 was released in June, and 1.5 was released in November. This is just a very small program running on the target platform, a ROM shell, which accepts commands over a serial port. Then there's a QEMU part of Serialize running on the host system and communicating with a ROM shell. So you use QEMU to run a factory BIOS. And memory accesses, most of the memory accesses, I/O accesses, MSR, reads and writes, and CPU ID operations, they go over the serial port into or over to the ROM shell and are actually executed on the real hardware. The results are read back to QEMU, and there's also a Lua interpreter included in Serialize, so you can do some scripting and filtering of all of these operations. Skip long loops and whatever you don't care about, and maybe set some magic values that are necessary to get the ROM to continue. All of this can also, thanks to the good debugging stuff in QEMU, you can also debug the factory BIOS using GDB. So that's really handy. And there was a question last year about JTAG and ICE, the in-circuit emulators that you might be able to use and that are common on embedded architectures, but they're not really very affordable for PCs. So this is not quite a replacement in every way, but it works in a lot of cases, and it's very useful to understand what's going on inside the factory BIOS if you're stuck. Many times the only alternative is to find out what the factory BIOS is doing. Same goes for the VGA BIOS, of course. CBIOS news, it got adopted by QEMU, and QEMU are actually going to use CBIOS as their default BIOS from version 0.12, I believe, and later on. CBIOS also has some USB keyboard support, and just recently got ATA DMA support. It runs Option Roms natively. You can have lots of them stuck or tucked into CBFS. It will run through all of them, and then it's going to make or show a nice boot menu if you want to, with all the devices found by these Option Roms or initialized by the Option Roms. So it's really very compatible to a BIOS. It does the exact same things. Just it's open source, and I think runs faster, as we'll see in a bit. Another nice thing with CBIOS is that if you put a few more payloads into CBFS besides CBIOS, you can get those payloads in the boot menu as well. And some more stuff happened, good stuff in libpayload. There was a GPL licensed Ohci driver. So the existing USB support in libpayload is UHCI, the Intel and VIA controllers. Unfortunately, this was licensed under the GPL, and some code from other GPL sources was reused, so it really can't be changed by the author. Since libpayload is BSD licensed, we can't really merge it, but we can keep the patch, of course, and for anyone who is okay with having a GPL licensed libpayload, they can use this driver and get USB support also on other hardware. Philo learned to do USB mass storage, and FlashROM had 2 releases. 0.90 in May with the works, just hundreds of flash chips and chipsets supported. And then 0.91 in September came out. And that supports external flashing as well. So not only the boot flash connected all the way down there, but it also supports flashing flash chips on network adapters and on the silicon image serial ATA adapters. And it also supports FTDI, some FTDI USB to SPI converters. It also specifies a universal external flasher protocol that is useful with a small microcontroller. And one good feature introduced in 0.91 is that it will now always verify when it has done write and erase operations. Previously, you had to do that manually, and yeah, it's nice to do that always. Finally, there's another new tool, BIOS Extract. It combines and extends all the previous BIOS decoders into a single tool. So previously there was AMI deco and Phoenix deco and Award deco, and now there's just BIOS Extract. Also, it supports some new AMI BIOSes that the AMI decode doesn't really support. And I wanted to say something about this boot timing measurement stuff that is getting more popular and showing up in marketing. There's really no standardization, so it would be nice to have this, and I think we could, of course, start doing some kind of formalized specification for how to measure boot times. It's important to really know what you're looking at or what the numbers are describing when you're looking at them, because there are about 30 voltages in a PC, give or take a few, and these need to come up in a specified order, and that takes time. It might not take seconds, but it still takes time. And also, are you, when you're measuring how fast the BIOS is, are you measuring from the very first instruction that the CPU fetches, or are you maybe measuring after you have the BIOS failover part executed? And yeah, what does this number really mean? So we had the CBIOS developer, the main CBIOS developer, Kevin O'Connor. He did some optimizing of CBIOS, and he did some tests and time measurements. He has an EPIA-CN board. It's a C7, I think 1 gig CPU, and the CN700 chipset. It's a mini ITX board. He's using coreboot and has a CBIOS payload in the flash chip, and then he put grub on a serial ATA solid state drive. So in his case, 350 milliseconds were spent on what seemed to be power sequencing, because there wasn't really any execution going on in the CPU as far as he could tell. Then 50 milliseconds waiting for the SM bus to initialize, this green thing, so that you can read the EEPROM from the DIMMs. 20 milliseconds to set up the DDR-ROM. 10 milliseconds for the coreboot code that does the PCI bus and device initialization. 200 milliseconds for running the VGA BIOS to get some graphics. Of course, that's just a blob, so we can't really change it. We just have to live with it. And another 10 milliseconds in grub, and in total that made 750 milliseconds from him pressing the power button until Linux kernel was running, and I think that's really good. And it's also because of this power sequencing or whatever is going on that is not CPU execution, because that is such a big part of this number, it's getting difficult to do much better, and that's exciting, of course. So, conclusion, this firmware stuff, I think it's an interesting problem. I mean, we have 30 years of hardware history in every PC out there, and we need to know how to rub it the right way. Kconfig makes it a lot easier to get started using coreboots. Even if you're only playing with QEMU and you're running it emulated, it's still very easy to get going. A lot of mainboards have the same components and are really similar, and this is a good way to get started with the development, to find a mainboard which is similar to something already supported. Serialize is a great addition. It helps understand what the factor BIOS does. As I said, the vendor documentation, even if we can get it, which we many times can't, it's never sufficient. We need to figure out what the other code is doing. And so coreboot on netbooks, or laptops in general, what's the big deal, or what's the status? So VIA VX800 and the Nano is being used. The combination is being used in a couple of modern netbooks, and I've bought this Samsung NC20 machine, which I'm working on. So I guess hopefully for FOSDEM. Let's see. So thanks to Alexander Klink for help with the preparations and getting me set up here, and all the Chaos Angles again for making this conference happen. We have the links, coreboot.org, mailing list, IRC on Freenode, #coreboot, coreboot.org/whatever, or check out Serialize or FlashROM or cbios.org. And maybe time for questions? A couple of questions, yeah. Yeah, let's.
Check. Test.
You said.
Check.
Okay, one question is coreboot FS writable by the BIOS?
Is coreboot FS writable? So the normal way you use coreboot FS is this CBFS tool utility, which you use to put files into a coreboot FS image, and then you flash that image to a flash chip. I see in the future that CBFS tool and FlashROM will merge somehow, so that you can do the same operation, but that you can do it directly on a flash chip. In theory, it's writable in Flash. Yeah, sure. But yeah. So does that answer your question? Okay. So there were two more, I think.
You said 32-bit mode was entered first before initializing RAM. How is it possible? What about descriptor and interrupt tables?
So can you please repeat the question?
How is it possible to enter 32-bit mode before initializing RAM?
How is it possible to enter
32-bit mode, protected mode on...
protected mode without RAM?
Yes.
Just set the bit. It works, yeah.
Okay.
Yeah. Set the PE bit. You can, you disable interrupts and you set up the descriptor, the GDT to match the cache's RAM configuration that you're going to use, and then it works. And as long as you don't access any RAM anywhere, the CPU doesn't know and doesn't care.
Okay, I have a question. You mentioned this thing with the serial output for the debug, and
yes.
Then you mentioned you have your netbook there and so on. How do you get the serial port on the netbook? Do you solder something onto a chipset, or where do you get it?
It's so sometimes you can find the right pads to solder on, but the way chipsets and CPUs work these days is normally or the capsules the packages that they come in is usually a BGA. So the connections are all underneath the chip and you can't really access them. In that case, you have to rely on the USB debug port, or maybe you can find some other communications method. So there's a socket for the RAM here, and the RAM has this green SPD memory. So maybe you can use that I2C bus to send out debug messages, or maybe you can use the flash chip accesses. If you have a ROM emulator, you can set it up so that if you read from a special sequence of addresses in the flash chip, that actually translates to a debug output write.
Okay, the way I see it, then you mean like for your development, you make a patch to see what you're actually doing. It's just because in the list of software you said there was like sort of a standardized serial output, but in reality, it's not really used the way you explained it there. You would do
it is on a lot of boards.
You would do whatever to see some sort of output from your particular.
Well, there is a standardized console driver, which is what the entire coreboot uses, and just outputs the console driver. And then what the console driver does behind the scenes, it can either be using a standard COM port, if there is one, or it can be using a USB debug port, as I mentioned, the programmed I/O on the EHCI controller, or it can be doing something else. But most systems either have a serial port or they have USB debug So we haven't really been forced to do any of these more creative solutions yet, but I'm sure we might have to do that sometime.
We are running out of time, so last question, please.
I was wondering if you could maybe highlight a couple of the facilities that libpayload would offer me as a developer for payloads. How fun is it to code libpayload? What can you do with it?
You can do whatever you want in the payload. You own the machine. You're the only thing running on the machine.
What does it give you? Library facilities?
There is no real... Oh, you mean libpayload itself? Oh, okay. Well, gee, okay. There's a console output. There's a PCI access... a PCI access library, there's NVRAM access, there's, what else is there? There's a graphics driver for GeoDLX and one for plain VGA. There's USB, some stuff. USB keyboard for sure, and of course PS2 keyboard as well. Serial port in out. I would have to check the source code. I guess we can look in a little bit and see what there is more. There's probably more as well that I don't remember right now.
One more question on the USB stack. I'm unclear about where the USB stack is sitting. It's in the C BIOS only? So the host support for USB keyboards, or?
Good question. There are several USB stacks, more or less thin. C BIOS has some USB support for keyboard, the early stuff. Philo and libpayload together, well, okay, so libpayload has a low-level USB stack, and Philo adds mass storage on top of that. And of course, the plan is to get that mass storage also configurable in libpayload, but for now, I think it's still stuck in Philo.
And the stack, is it polling or is it interrupt mode? Is it busy polling? Is it running in SMM?
I'm not sure. I would have to check.
I'll read the source, okay.
Yeah, of course, read the source. I'm not sure. No, I don't want to say. It could be interrupt driven, but I sort of doubt it. I think it's polled. I'm not completely sure.
Are you by default using SMM mode in any?
No,
okay.
no.
You're leaving it untouched, you're not locking it?
It's, by default, it's not touched at all, so it's not locked. And most boards do not enable, do not use it. So it's free to use for payloads or whoever comes next. There are some boards that require system management mode support. So the GeoDLX is one example. It has the VSA, the virtual system architecture stuff, which is SMM. So their coreboot does initialize the SMM and sets it up and locks it as well. And also one or two Intel boards, or boards with Intel components are using SMM and should have it locked as well.
But then you write the SMM handler yourself, or you
Yes.
just copy it? Okay.
Yes. So there are two SMM handlers in coreboot. There's the geode, the VSA stuff. Well, actually, that's not part of coreboot, but the source code is available and it's used by coreboot. And there's the one for Intel platforms. No? I can repeat the question.
Okay, for starters, version 2 I think is what you recommend, but then should I go on, have a look at version 3, or should I wait for version 4?
So, okay, good question. Should I recommend version 2, but is it useful to also have a look at version 3, or should one wait for version 4? What used to be version 2 is really going to become version 4, and I guess it's already on good way. Version 3 is definitely interesting to look at, and especially if you're using AMG GeoDLX hardware, then it's what you should use, I think. Otherwise, focus on the current trunk, the old version 2. Okay. I got the head cut off sign, so I guess it's time to go, and they also closed the projector. Thank you very much for coming and listening.